Hey everyone, in this video I'll be going over the Leetcode problem Jump Game 2. So in this video I'll be introducing the problem, explaining how the solution works, implementing the solution, and then analyzing the runtime. So this problem gives you an array of numbers, and each number in the array represents how many spots you can move forward in the array. So for example, if I'm positioned here at this index, I can move forward 1 spot or 2 spots. And so you're initially starting at the first index, so you initially start here. And yeah, so your max jump length, that's just how many spots you can move forward. And you want to move forward until you get to the last index with the fewest number of jumps. And it's always possible to reach last index. So in this example, you would want to move forward 1 spot because you have 2 jumps, so you want to move forward 1, and then with these 3 jumps, you can get all the way to the end. So you need 2 of these jumps to get all the way to the end. And so we can solve this problem using dynamic programming because, yeah, let's just get into explaining how the solution works. So let's just say we have an array, and this array will keep track of how many jumps it will take from each spot I to reach the end, okay? So what we can do is we can start and have all these numbers be infinite because as far as we know, it's not possible to reach the end yet. And we'll set all those to infinite, and we'll set the last one to be equal to 0, because if we're at the last one, that means we don't need to do any more jumps to reach the last one. And then what we can do is we can look at our array of jumps, and starting from the second to last one, we say for every possible number of jumps inside that we can take from this index, can we reach the end? Well, of course, if the number is greater than 1, so like 2, of course, we can just move forward 1 spot and get to the last index, okay? So then in our DP array here, dynamic programming array, for our second to last number, we'll say 1. Yes, if we ever land on this spot, we only need to do 1 more jump to reach the last index. And then we can go to the next one. So for every number of jumps here, let's just say you can do 2 jumps again. We see what's the best case scenario for us if we do that many jumps. So we try doing 1 jump. So 1 jump, we land in this spot. Well, we already calculated how many jumps it takes to reach the index from this spot. It takes 1, like we see up here. So because this is originally infinity, we know we have found a better answer than than infinity, because we can move to this spot and then from this spot do 1 move. So this would be this spot added 1. But then we would try moving forward 2 spots, and we see, oh hey, this spot is 0. If I get to this spot, I won't need to do any more jumps. So then our answer, instead of being 2, it'll be 1, because it'll just be 0, because once we reach here, we don't need any more jumps, plus the 1 jump that we take to reach that spot. So yeah, and then same thing with here. So let's just say we have another thing of 2. We can, if we ever reach this spot, we can move forward up to 2 spaces. So then here we would do the same thing. So we would try moving forward 1 spot. Oh hey, if we move forward 1 spot, we know this spot we end up at, it'll take us 1 more jump. If we try moving forward 2 spots, same thing. So the best case scenario is where if we land at this index, wherever we move, we will need 1 more jump to get to the end. So then it'll be that 1 extra jump plus the jump that we take to get to that spot. So this would be 2, because it'd be 1 plus 1. And we can just do that for all these spots until we get to the first one, and then we'll know how many jumps it'll take. We'll know the minimum amount of jumps it'll take to get to the last index from the first one, because we'll just sort of build on our information that we know. So we start from here, and every index that's closer to the start of the array will build on the information that we've already calculated, because we can just see, hey, instead of having to calculate, oh, I need to do exactly these jumps, I can just say, I can just look, if I move here, well, I already know how many jumps it'll take to get to the end from this spot, so I can just check the spots right in front of it. So let's get into how this would be implemented with code. So in this solution, let's first just create our DP array that we're gonna use. New int array nums.length. So this will store how many jumps we need to reach the end if we're at that index in our DP array. So first we'll fill up all of these with a really large number, and I think it says here, yeah, num.length is between 1 and 1,000, and since you know it's always possible to reach your last index, the worst case scenario is you have to perform like 1,000 jumps moving forward one spot every time. So we can just say int I equals 0, I less than dp.length, I plus plus. We can just fill up this array with a large number that we know is not gonna, like, it's gonna be pretty much infinite. So let's just say that equals 10,000. So now what we can do is we can set the last guy equal to 0, because if we know we are already at the last index, we don't need any more jumps to reach the last index because we're already there. And now we do our algorithm by checking each spot after the last index and then computing how much and then building up our array. So int I equals nums.length minus 2, because num.length minus 1 will be this spot, so we'll start at this spot. And I is greater than or equal to 0, I minus minus. So now we'll be going through the array in reverse order. And now nums, so the number of jumps, I'll call this num spaces. So this variable will represent how many spaces we can move forward in the array. So it'll be nums I. So we can move forward this many spaces. So for int j equals 0, we'll call it 1, because you always want to move forward one space at least. And then j is, while it is less than or equal to the number of spaces you can move forward, we will try moving forward that many spaces. And then we'll put that information here. So we'll call this the number of jumps. So int num jumps, that will equal 1 plus what we've calculated before, dp I plus j. So this spot represents how many jumps we need to reach the end from the spot that we choose to jump to, and then add 1 because we need to jump to that spot. And yeah, and we should probably include a check here. If I plus j equals the length, so minus 1, that's the last index, so we'll just break out and set this equal to 1. Whoops. And then here we'll just say, here's the number of jumps we need to get to the end if we jump forward to j spaces. So now we will just say this index here will be equal to the minimum of itself and the minimum if we jump forward that many spaces. And so yeah, I believe that this should be it. And then at the end, we can just return how many jumps it will take if we start at the first index. So yeah, let's see if this works. I don't think there should be any bugs here, but I could always have typed something wrong. Wrong answer output. Let me debug this. Whoops, I think I've just made a silly logic error. I should be setting this because that's the number at that index. And yeah, so all these should just be DPI here. Yeah, but this one should be I plus j. So let me just run this code against their test cases to make sure it works. Use sample test cases. Alright, yeah, because you don't want to be checking I plus j here because DPI is the index that we're currently at, so this is how many jumps we need from our current index. So let's submit this and hope that it works. And beautiful. So it works. This runtime is the fastest it can be because it is a O of n, because we're just going through the entire array once. And yeah, so I hope you guys enjoyed the video. That's it. Yeah, so this was the solution to the problem Jump Game 2, and we can solve this using dynamic programming. And yeah, I hope you guys enjoyed the video.